We will start today with another characteristic property of transition elements, and that property is nothing but it is actually called as complex compounds. Or the question which arises or which is asked basically is that why do transition element form complexes? This is the point. Formation of complex compound. See, first of all, the point is what are basically complexes are. ये complexes क्या होते हैं? So there is a chapter basically which is actually called as, of course, called coordination compounds. In P block also we have done one of the reaction where Cu, copper, NS3 whole 4 2 positive, which was of course intense blue in color, right, was one of the coordination compound that was formed when copper react with ammonia. Now the point right now here is, here this ammonia is acting as a ligand, or it is also called as a Lewis base, where it is capable of donating the electron to the central atom, of course the d block element, because of vacant d orbital, and forming a coordinate covalent bond. This is a coordinate covalent bond which is being formed. Few more examples that we have done was NiCO4, where of course nickel is in zero oxidation state, or FeCO5, where also it is in zero oxidation state. I can take up n number of examples, and the point right now is, the only question is why do transition element form complexes? So the point why transition element form complexes is due to the small size of the atom and the ions of transition metals, of course the availability of d orbital, which have suitable energy to accept the lone pair of electrons from the ligands, which as I said is nothing but it is the Lewis bases, and the most important is high nuclear charge, or also the tendency to attain variable oxidation state. I repeat, transition elements are capable of forming complexes because of their small size, of course the atom or ions, availability of the d orbitals, right, which has approximately the same energy of the ligands to accept the lone pair of electrons, high nuclear charge and variable oxidation state, because of which they form complexes. There is another point that I have to take up, and that is, why do transition element act as catalyst? See, when I'm talking about why do transition element act as catalyst, another characteristic property of transition element is that of course they act as very good catalysts. See, when I'm talking about that why exactly they act as catalyst is again dependent on one of the most important thing, and it is exactly called as what? Tendency to obtain or attain variable or multiple oxidation state. I repeat, transition element, due to the presence of variable oxidation state or due to multiple oxidation state, which provide a greater surface area for the reactants to get adsorbed onto the surface of the d block element, thereby increasing the number of the collisions to convert the reactant into the product. If you remember beta, in surface chemistry we have already done that if there is a graph which is being plotted in between potential energy and the progress of the reaction, ये reactants हैं, ये products हैं. Reactant can be or are converted into the product because reactant have higher potential energy, products have a lower potential energy. But as I said, this red is nothing but it is basically an uncatalyzed reaction which has a higher activation energy. But if I am using a catalyst, catalysts provide the shortest path by giving larger surface area, and by providing the shortest path, lowering the activation energy, it convert the reactant into the product. ये इसलिए पॉसिबल होता है बिकॉज ऑफ व्हाट? ये किस लिए पॉसिबल होता है, ये क्यों पॉसिबल होता है? बिकॉज ट्रांजिशन एलिमेंट के पास वेरिएबल ऑक्सीडेशन स्टेट होती है. आई रिपीट, ड्यू टू वेरिएबल ऑक्सीडेशन स्टेट, of course they act as very good adsorbent, and of course since they have multiple oxidation state, as I said they have multiple oxidation state, and they provide larger surface area, So the reactants are being converted, right, into the products very easily, right? And that's why rest you write anything will not make any difference. The only point is that due to variable oxidation state, they act as very good adsorbent, and they of course adopt multiple oxidation state, provide larger surface area, so that by the shortest path the reactant will be converted into the what products. So this is one point. There is another property, and it is exactly called as the magnetic property. So the third property which I am going to discuss right now is nothing but it is called the magnetic property, right? The question is, why do transition element has a tendency to show magnetic property, right? So when I'm talking about magnetic property, transition elements are usually paramagnetic. Paramagnetic means they must have unpaired electrons. Unpaired electrons. Now, as I have already told you, if this is nucleus, this is your, suppose, n minus 1d penultimate shell, and of course this is your the outermost ns. As I have already told you, ns and n minus 1d, that means the outermost shell and one inner to the outermost, that's called penultimate shell, have almost compatible energy. Due to this, there are large number of unpaired electrons, and if there are unpaired electrons, that means it will always act as paramagnetic. But right now the point is, the magnetic property of any substance is exactly being predicted on the basis of one thing which is exactly called mu total. So ये जो mu total होता है, इसे हम बोलते हैं magnetic moment. This is called magnetic moment. Magnetic moment, right? Now magnetic moment is nothing but it is always equal to mu spin plus mu orbital. I thought we have already done, एक्चुअली हमने फर्स्ट चैप्टर में ये कॉन्सेप्ट किया नहीं है, बट एन इलेक्ट्रॉन इज नॉट ओनली रिवॉल्विंग अराउंड द न्यूक्लियस. एक इलेक्ट्रॉन जो होता है, आपने सुना है, इट इज नॉट ओनली रिवॉल्विंग अराउंड द न्यूक्लियस बट इट इज ऑल्सो रोटेटिंग ऑन इट्स ओन एक्सिस, राइट? सो उसकी वजह से जो मैग्नेटिक मूवमेंट होता है वो दो चांस या दो प्रोबेबिलिटी होती है जिससे आ सकता है. वन इज एक्चुअली कॉल्ड एज म्यू स्पिन. म्यू स्पिन जो है वो तब आ रहा है जब एक इलेक्ट्रॉन अपनी एक्सिस पे रोटेट कर रहा है, राइट? और अगर ऑर्बिटल मोशन की बात कर रहे हैं तो ऑर्बिटल मोशन आता है जब वो न्यूक्लियस के आसपास, राइट, चक्कर काट रहा है. सो व्हेन वी आर टॉकिंग अबाउट दिस म्यू ऑर्बिटल इज नथिंग बट इट इज क्विंच्ड. सो व्हेन यू आर टॉकिंग अबाउट द क्विंचिंग का मतलब होता है सप्रेस हो जाना. सप्रेस इसलिए होता है बिकॉज डी ब्लॉक एलिमेंट जो होते हैं वो बेसिकली क्या होते हैं, देयर शील्डिंग इफेक्ट इज वेरी पुअर. तो अगर मैं म्यू स्पिन की बात करूं, यानी दैट मीन्स म्यू टोटल is actually equal to mu spin. एंड ये जो म्यू स्पिन कैलकुलेट करने का फॉर्मूला होता है बेटा, दैट्स ऑलवेज इक्वल टू अंडर रूट n plus 2 bm, where bm is nothing but it is exactly called as Bohr magneton. I repeat, it's called Bohr magneton. ये जो Bohr magneton है ना बेटा, this is the unit of spin, where as I said n is nothing but it is equal to the number of unpaired electrons. So अगर आपको number of unpaired electrons पता है तो it is possible that you can calculate the magnetic moment of any element or any, right? So this is given here. It is calculated by mu spin, that is under root n plus 2 Bohr magneton, that we have already done. Now there is a question on the basis of this. So that question of course I'll take up. Now the question is this: calculate the spin only magnetic moment of M2 positive aqueous ion. Z is given as 27. So this is Intex 8.8. So if I'll take up Intex 8.8, see the question is M2 positive ion is given to you. The Z is given as 27. So if whatever, if Z is 27, that means the configuration will be what? Argon 3d7 4s2. ये मैंने आपको पैलेंड्रोम का कॉन्सेप्ट बताया हुआ है कि अगर यहाँ 27 है तो यहाँ 72 हो जाएगा. Since it is M2 plus, that means the 2 electrons will be removed from here If it is removed, argon will be 3d. How much? 7. So if I'll try to put 3d 7, so this is d subshell. D subshell के अंदर we have done that there are 5 orbitals. 5 ऑर्बिटल में अगर 7 इलेक्ट्रॉन्स रखेंगे जाएंगे 1 2 3 4 5 6 and 7. Now what? There are 3 unpaired electrons. So the value of n is 3. So if I ask you what is mu total, of course that is equal to under root n plus 2 Bohr magneton, that will be under root 3, 3 plus 2 5. So that means under root 15. अंडर रूट 15 का मतलब मैं अप्रोक्सीमेटली 3.87 के आसपास बोहर मैग्नेटॉन लिख देता हूं. ऑल्दो अंडर रूट 15 जो है ना अप्रोक्सीमेटली 16, अंडर रूट 16 जो होता है वो 4 होता है, तो मैंने थोड़ा सा कम करके लिख दिया. इफ इवन यू राइट 3.9 ऑल्सो, दैट्स ऑल्सो वन एंड ओनली द सेम थिंग. सो यू कैन राइट एनीथिंग वॉट एवर यू लाइक. द नेक्स्ट पॉइंट दैट आई हैव टू टेक अप राइट नाउ is formation of colored ions, a very important topic that I'm going to take up right now. That why do transition element have the tendency to form colored ions, right? So I thought I have already taken up these questions, like name a transition element which does not have variable oxidation state. Of course, scandium, which shows only +3 oxidation state. Then I have also taken up this question, which metal in the first transition series has +1 oxidation state more commonly. I've already told you it's not chromium, because most of the time people used to write chromium. It is copper. Copper is stable in +1 oxidation state, of course, because it has a 3d10 configuration. But in aqueous medium, you know that it is always copper 2 positive, which is more stable rather than copper 1, right? Because copper 1 has a tendency to disproportionate into copper 2 positive and copper in solid. This also we have done. Now, another question is, calculate the number of unpaired electrons in the following. So this is also a very simple question, how to calculate the number of unpaired electrons, and then which of these is most stable in aqueous solution. So Mn3 positive, Cr3 positive, vanadium 3 positive, titanium 3 positive. So Mn3 positive means configuration of, this is the manganese key configuration. If you will remove the 2 plus 1, 3 electrons, you will be having 4 unpaired electrons. Chromium 3 positive, 3d5 4s1. This is the configuration of chromium. Chromium 3 positive means what? 1 from here and 2 from here. So 3d3, 3 unpaired electrons. Vanadium 3 positive means this is vanadium ki configuration, 2 from here, 1 from here. So 3d2 configuration, 2 unpaired electrons. And titanium, of course, will have 3d1, so 1 unpaired electron. As we know that chromium is always stable in half-filled T2G orbital configuration. I repeat, as we know that chromium is always stable in half-filled T2G orbital configuration. That's why chromium is the most stable in aqueous solution, because as I said, it has a half-filled T2G orbital configuration, which is a keyword for this. This is the keyword, right? One of the most important property of transition element is that they always form colored ions. You are already aware that copper 2 positive, blue in color, Mn2 positive, pink in color, Fe3 positive is brown in color. Now the most important is even the MnO4 negative, which is of course permanganate ion is purple, dichromate ion is nothing but it is orange. These all are nothing but these are basically called as, these two are basically called as oxoanions. That means anions which are actually being formed with oxygen. Now I thought I have already told you that this is a d subshell which has 5 orbitals, and of course you remember that dxy, dxz, dyz, in the beginning of the chapter I told you this is called T2G, dx square minus y square and dz square is called as Eg orbitals. So these are 5 degenerated orbital. Degenerated orbital, I hope you know, which have equivalent energy. Now the point here is, or the question is, why do transition elements show color? Answer is very simple. See, these are degenerated orbital. Degenerated, as I said, degenerated means which have equivalent energy. So they all have equivalent energy. Now when they have equal energy, when the ligands are not approaching them, d orbitals की energy तब equal होती है when the ligands are not approaching them. When the ligands are approaching them, you will find that it will try to split up into a set of two non-degenerated orbitals. Although this chapter, this topic is again going to come in coordination compound, but let me take up in a very, I mean, a simple way, that this is now these are non-degenerated orbitals, non-degenerated. Now you may ask me, what are non-degenerated? That means which do not have equivalent energy as degenerated orbital will have. And this is only possible when the ligands will try to approach. Now what will happen if any transition element has unpaired electrons? अगर किसी भी transition element के पास unpaired electrons है, so you'll find that what will happen, the electron will go from the ground state to the excited state. Again it come back to the ground state. This transition is basically called as DD transition. I said this transition is called DD transition, and anything which has the tendency to show DD transition will always show you color. What I mean to say here is कि अगर suppose ये देखिए, ये रहा एक d orbital, यहाँ ये degenerated नहीं है, अब ये non degenerated हो गया. When the sunlight will try to fall over it, if they have unpaired electron, it will try to go from the ground state to the excited state, and once again come back to the ground state. DD transition is possible, it will show color. So now let me take up what I have written for the color in my notes. I have written that, see, the transition metal in the elemental form or ionic have, if they have one or more unpaired electrons, and when the light will try to fall over it, of course the electron will try to go from the ground state to the excited state, and due to DD transition it is going to show you the color. However, the most important point right now is, if the ion does not have any unpaired electron, so it will always be what? White, or it will be colorless. So let us take up the example. For example, zinc 3d10, cadmium 4d10, mercury 5d10. They do not have any unpaired electron. There is no unpaired electron. That means there is no DD transition. So they will always exist in white color, or they are always colorless. I'll keep on giving you the examples. For example, if I'm talking about scandium 3 positive, titanium 4 positive, vanadium 5 positive, they all have D0 configuration. That means there is no unpaired electrons. No DD transition is possible. Of course, again, they are white or they are colorless. There is another very good example, which of course have been asked n number of times in board. Why scandium aqua complexes? I repeat, why scandium aqua complexes? If you see, scandium aqua complexes are colorless, while titanium aqua complex are nothing but they are colored. Why? If you calculate the oxidation number of scandium from here, what you will find, x plus 6 into 0, because water के ऊपर कोई charge नहीं होता बेटा, and is equal to plus 3. So x is plus 3. So scandium atomic number 21, argon 18, even if you won't write 18, will not make any difference as such. Argon 3d1 4s2. That means scandium in 3, as I said above also, scandium in 3 positive will have what? 3d0. So there is no unpaired electrons. That means it has no DD transition, no color. But on the other hand, if I'm talking about what? Titanium. Titanium aqua complex is colored white. Again, titanium also has plus 3 oxidation state. Titanium is atomic number 22, argon 3d2 4s2. Titanium third means 3d1. There is one unpaired electron, and that's why it is capable of showing you DD transition. It is capable of showing you DD transition, and since it is showing DD transition, it will show you color. Now, as I said, we have already discussed this question, calculate the number of unpaired electrons, right? The question which is asked from here is this: predict the number of predict that which of the following will be colored in aqua solution. Of course, it depends upon the number of unpaired electron. For example, titanium is atomic number 22. Titanium 3 positive it is asking. So titanium 3 positive means 3d1. So it will be colored because it will have, of course, DD transition. Vanadium 23, vanadium 3 positive will have 3d2. Again, it has unpaired electron, so it will be colored. Copper 29, copper 1. Of course, the configuration is 3d10. No DD transition is possible. That means it will be colorless or white. Of course, copper 1 salts white ही होते हैं. Scandium 3 positive. Of course, 3d0. No DD transition. Again, colorless or white. Manganese Mn2 positive. आपको कलर याद करने की जरूरत नहीं है, right? If I am talking about manganese, Mn2 plus has 3d5 configuration, right? Of course, Mn is also stable in plus 2 oxidation state. So it is colored. We have done that. It is pink in color. Just now I told you. Fe, Rn is 26. Argon and 3d5. 3d5 means again unpaired electron. dd transition is possible. Colored. और हमने पढ़ा Fe3 plus जो होता है वो brown होता है, ferric. Cobalt 27. Cobalt 2 plus is 3d7. So colored. Peacock color होता है बेटा इसका. My next property of transition element is that they have a tendency to form interstitial compound. Now, I was talking yesterday that interstitial compounds are basically those. Suppose this is the lattice. This is the lattice of your D block elements. These are the voids which are present over here. These are the voids, also called as interstitial sites or so I was telling, if these are interstitial sites or voids, the small atoms like hydrogen, carbon, nitrogen, boron, they all have a tendency to occupy over here. If they try to, or if they will try to occupy this position, you will find that they are capable of forming the interstitial compound. Of course, they all are, or most of them are nothing but they are non-stoichiometric compound. One of the best example is tungsten carbide. Tungsten carbide में basically क्या होता है? Of course, these black lines are nothing but they are showing the tungsten, and these voids are nothing but they are occupied by carbon. And tungsten carbide is the strongest, or it has a very high tensile strength. Now, as I said, the question is, why do transition element form interstitial compound? I said because the small atoms like hydrogen, carbon, nitrogen, boron, etc. have a tendency that they can be easily occupy the voids, and that's why they form non-stoichiometric compounds. One of the best example is tungsten carbide, titanium carbide, etc., etc., etc. There are so many examples, right? They can be ionic, they can be covalent, typically ionic, nor covalent, depend. It all depends. The next property is, why do transition element form alloys? You know the definition of alloy. An alloy is a homogeneous mixture of a metal with a metal or a metal with a non-metal. Transition element form alloy. Let's start with an example first. See, the example I'm going to give you right now is, first example is brass. The next example is bronze. So, see, both brass and bronze, both are nothing but they are the alloy of copper. And I always used to give a shortcut. ये देखो, यहाँ zinc आ रहा है, cross multiply, यहाँ zinc, और यहाँ S आ रहा है, तो ये 10 हो गया जी. That means brass is an alloy of copper and zinc, and bronze is an alloy of copper and tin. Now, if suppose this is a transition element where this black is nothing but it is exactly what? Copper. And what I have done, I have replaced this copper with what? Zinc. मैंने copper को क्या किया? Zinc से replace करना start किया. So if I ask you why I have replaced copper with the zinc, or how it is possible to replace copper with the zinc, the answer is very simple. That due to the similarity in the size of the copper and zinc, you are able to replace copper with the zinc. And since the size are almost similar, the other characteristic property also become same. Or I can say transition element form alloy due to the similarity in their size, and of course the other characteristic property also become constant. That's why they are capable of forming the alloys. Now let's start with the questions, as we have already done exercise 8.5. 8.3 also we have done, that which transition element has the highest oxidation state, manganese. Then these all questions we have already done. These all questions we have already done, so I'm not going to discuss all of them. In fact, why scandium aquo complex is colored, we have done. Now I'm going to take up the most important question, and that question is which is a stronger reducing agent, Cr2 positive or Fe2 2 positive? This is another very, very important question. I've written 2 answers for it. So I'll take up first. See, when I'm talking about Cr2 positive, let's first take up Cr2 positive. And I'm asking which is a better reducing agent out of it. If I'm talking about Cr2 positive and if I'm talking about Fe2 positive, both have the tendency to get converted into Cr3 positive. This also goes to Cr3 positive. This goes to Fe3 positive. See, when I'm talking about chromium in 3 positive, the configuration of chromium, as you know, is argon 3d5 4s1. So if I write Cr2 positive, configuration is argon 3d5. Cr2 positive will be 1 from here, 1 from here, 3d4. And if I'll write down it as Cr3 positive, it is argon 3d3. So you can see from here it has half filled T2G orbital configuration. But if I'll write down the configuration of iron, iron is argon 3d6 and 4s2 क्योंकि atomic number 26 है. So chromium of course is atomic number 24. तो palindrome यहाँ नहीं लगता क्योंकि half filled configuration होती है. आयरन में ऑफकोर्स पैलेंड्रोम लगेगा 62, 26 का 62 हो गया. If I write down iron in +2 oxidation state, it will be argon 3d6, and if I'll write in Fe3 plus, it is argon 3d5. So the point here is this is 3d5. The point here is this is 3d3. This is 3d5. The most important thing is, sir, why did you said chromium 3 positive is more or better reducing agent? The answer is क्रिस्टल फील्ड थ्योरी के बेस पे मैं आंसर दे रहा हूं बेटा. दैट इज इफ आई हैव 1 2 3 4 5, these are degenerated orbital. When the ligands will approach, as I said, it will split up into a set of non-degenerated orbital. This is T2G and this is of course EG. Same thing here also. Here also it will be divided. Now what will happen? See, if I have to take up or if I have to take fill these 3 electrons, it can be easily filled over here. 1 2 3. But suppose if I have to fill the 5 electrons, अगर मुझे ये 5 electrons fill करने हैं, किसके लिए? If I have to fill up the 5 electrons for iron, you will find that those 2 electrons has to go to the above, which require more energy here. So that means you will find it need greater crystal field energy or it need greater energy. That's why Cr2 positive is a better reducing agent than Fe2 plus. I've written D4 to D3 occur in case of Cr2 positive to Cr. It is easy to attain half filled T2G configuration as number 1 E naught value is negative. So it is a good reducing agent. You can write even answer on E naught value, that is also valid. D5, of course, E naught value is positive, so it will be a better oxidizing agent and not a good reducing agent. In aqueous medium, D3 is more stable as compared to D5. We will, as I said, crystal field theory में जो मैं अभी आपको बताने की कोशिश कर रहा था कि D5 में unpaired electrons करना difficult होता है और वहां easy होता है. So you write in any way, that is one and only the same thing. Question number 18 we have already done. Now the most important question is, why copper 1 is not stable in aqueous solution? हम already पढ़ चुके हैं copper 1 aqueous में इसलिए stable नहीं होता. The reason is because it has a tendency to disproportionate into copper 2 positive, which has a higher negative enthalpy of hydration. The higher stability of copper 2 positive in aqueous is attributed to greater negative hydration enthalpy. This question we have already done earlier also when I was discussing the previous topic, and as I said, it will compensate for the even the second ionization energy. यानी copper 1 से copper 2 positive में जाना बहुत difficult होता है, एक बहुत high ionization energy लगती है, but still copper 2 positive की hydration energy इतनी ज्यादा होती है या इतनी ज्यादा negative होती है कि वो उस second ionization energy को भी compensate कर देती है. Next question sample paper 2008 का है, transition catalyst. Chromium has the highest melting point, करा चुका हूं. Transition metal form colored complexes. This also we have done. Now, there will be few things we will be discussing about oxo anions, but not now.